Okay, so good morning, everybody. The topic of today is how we are going to simulate processes, so chemical reactions or conformational rearrangements on whatever that you can put in the category of processes that need to be activated. So typically when you do an electronic structure calculation, you're looking at the geometry of your system in its in a potential minimum, the potential surface minimum, but that's obviously already something interesting, but often we want to know how the system can then transform to one equilibrium state to the next, and which is the mechanism for this transformation, and which are the energy barriers that are involved. And to do that, since we have an n-dimensional system, so with n particle is actually a 3n-dimensional system, the potential surface that we have to explore is in general very complex, and the typical thing that is done is to try to reduce the dimensionality, like to find some coordinate that to follow in order to be able to describe this process. In doing that, obviously we neglect processes that might involve other coordinates, so we are already simplifying the system. So this said, if we know the barriers and the difference in energy between this equilibrium state and some transition state, assuming that we can define a reasonable transition state, let's say first order transition state where only one coordinate is involved. So if you look at the dimensionality of the system, only in one dimension you have a maximum, while in all the other dimensions you have a minimum. Obviously this is a very simplified case with only 2 dimensions. Then you can evaluate the energies and also the vibrational frequencies, and then you can give an estimate of the rate constant, and that is what you can compare in general with experiment. There are many ways to try to find these pathways. The common goal is to obtain the intrinsic reaction coordinates. So really the most efficient way to describe what happens to the whole set of coordinates that you have, and this reaction coordinate should be the one that following the minimum energy pathway minimize the total energy along the entire pathway. So if you have this information, so this reaction coordinate described in terms of your particle coordinates, then you can in principle construct the pathway yourself and follow the change in energy along this pathway. So then you find the barriers and whatever you need. We are always talking about potential energy surfaces. The problem is that, but for the most simple systems, this reaction coordinate is absolutely not trivial to find. So, okay, if you have a conformational change that involves a dihedral rotation, then it is obvious. But if you have a condensed matter system of molecule, a solute in a solvent, for example, and then you have to take into account all the degrees of freedom of the solvent of the molecule and maybe interactions with other solvent molecules, the reaction coordinate is not something that you can easily figure out. Though the definition of the minimum energy pathway is clear, so it is the pathway along which the gradient of the energy perpendicular to the pathway is 0. So the pathway, along the pathway it is not 0, but in the perpendicular dimension, so in the 3n minus 1 dimensions, this gradient of the potential energy is 0. So it is then a one-dimensional pathway, And yeah, and along this pathway you find the intermediates and the transition states. It might be a pathway that encounters more intermediates and then therefore more transition states, depending where are your reactants and where are your products. This said, we are working now, or often one works with potential energy surfaces, so the entropic effects are often not taken into account in this picture, and that might involve additional, so extensions to the definition of the problem. And yeah, but though once you have this minimum energy pathway, then, or when you have at least an estimate of the minimum energy pathway, it is easier to, by minimization, to find the intermediate states, so with more accuracy. If you find a transition state and you sit on this transition state, so you put your system in at the transition state and then you minimize, then you should be able to find the minima, so the equilibrium state that are connected to this transition state. So that's a check whether the transition state is well defined. There are also here many different approaches that can be used to find the minimum energy pathway. The most successful for at least simple systems where few coordinates are involved are those that use the elastic band. This is something that has been proposed already many years ago. So you have some reactants and products, you interpolate among them with a pathway and you define some intermediate configurations. So you define like a band with beads or images. And the goal is to minimize the energy along the band such that the beads remain more or less equidistant. So this is can be easily done. So this is the energy along the pathway. So and you put some sort of a constraint on this distance among the two sequential, so two consecutive beads. You start with an initial gas. The initial gas can be really trivial, so simple, like in linear interpolation between the two final states. You need to have final states, and then you can try to optimize this path. And so if you start from this green line, you should instead end up with this blue line that follows indeed a lower energy profile. The minimization, as I said, it's done keeping some constraints, so such that this distance between the two consecutive beats is more or less equivalent along over the path. And this is done because you are doing optimizations at each bead, and if you don't put any constraint, obviously every bead would fall to the minimum. That means that in your minimization, so you have a constraints optimization at each bead where you have the forces that come from the underlying potential energy surface and some forces on each atom that come from this spring potential, this constraint potential, restraining potential. This you can do with CP2K, obviously, and the way to do it is to have in the motion, I think run type is band, and in the motion then you have the band section, where in this very simply, so the first method we described, this is the elastic band. You write here band type EB, and then you can give how many replicas you want along your path, which is the spring constant, so for this restraining potential, and other important keywords here are whether or not you want to align in the first guess of your frame. So you rotate them such that you minimize the root mean square displacement among the configurations. So this is aligned frame. And whether you want to rotate them over the process. So at every step of the NEB, of the EB, in this case, you rotate such that you minimize again the root mean square displacement. This type of simulation are easily to parallelize. So if you have many processors, you can assign to a bunch of processors the different replicas. So then this is really linearly scaling, and then you can here say how many processors you want for each replica. It is important that you have a commensurate number of processors if you do that, because if it cannot be equally distributed, then you will have some processor that might do crazy. So they do things that they don't know what to do, and then they finish their calculation, and then they start repeating calculation that should be done from other processors, and that might cause problems. So but this is easy to do. If you have 32 replicas, you want to have a multiple of 32 number of processors. That's obvious. You give the coordinates of at least 2 configurations. If you just give 2, that will be the first one and the last one. If you give more, then the one in between will be something that are in between the reactant and the products. If you just give 2 and then you require 32 replicas, the other 32 will be automatically generated by the code, just making interpolations and trying to keep this equidistance. The equidistance is calculated according to the root mean square displacement. The replicas you can give by file name or just giving really the coordinates here. Yeah, what else? So that each one is a geometry optimization, so you have to give some threshold so that it is understood when the geometry optimization is achieved. And you can define how to optimize it. A typical method is DIS. In principle, you can do also quenched molecular dynamics to minimize. So that you make some sort of annealing, you start with some temperature and then you reduce to 0 the temperature, and it's a sort of a minimization scheme. Optimize endpoints, yes or no? Well, if you have them already optimized, you can avoid optimization of the endpoints. Okay, that's for the elastic band. The elastic band in itself, so it's a quite simplified scheme, and it showed immediately some some problems, and they are related to the comparison between the forces along the path, so they say the parallel forces, and the forces perpendicular to the path. And if you have a spring that it is too rigid, then you typically have, so too hard, then they typically have rigid bands that cut out corners, so they don't follow maybe the topology of the potential energy surface with enough flexibility, because it is, so the distance is too strongly kept constant, and they don't have this flexibility. If the K, so the spring constant, is too small, then the beads tend to slide down towards the minimum, and then you don't have also a good description of the transition states. Okay, and that's the sliding down is due to the parallel part of the force, so the parallel to the band, and it comes from the potential energy surface, the underlying potential energy surface, while the cutting corner comes from the orthogonal component to the forces, and it depends on the spring potential. So the next and most used method in this family of methods use elastic bands is the one that introduces a projection of the forces instead of using the total gradient to calculate the forces, so the gradient of the potential energy surface and the gradient of the spring potential. It, for every component, for every contribution, it is distinguished the parallel component and the perpendicular component to the path, and then you use you remove the sliding down component so that it is the parallel component from the underlying potential, and the cutting corner component that it is a perpendicular component of the spring. This method is very well known and is the nudged elastic band method. And there are several flavors of the nudged elastic band method, and they differ by the definition of the tangent to the band at each bead position, at the image position. So the first definition was simply something like that, that takes the tangent at I is given by this normalized difference between the position at I plus 1 and at I minus 1. And this is the NEB, the nudged elastic band forces, where you see that there is the tangent component here is removed, and here there is only the perpendicular component of the spring potential. Other methods are the B-NEB, so the bisection NEB, where you see here how the tangent is defined. This has been shown might have some effects on the presence of kinks along the path if the spring parallel force is much larger than the perpendicular potential force. So to improve and to make smoother pathways, the improved tangent method has been introduced. You have here the formula. In fact, you define differently the tangent depending on the shape of the band at your bead, and this provides a smooth switch of the definition of the tangent when you are in situation like here, so that's where you really change from a growing to a decreasing band. And this guarantees sort of a really equal and uniform spacing along the band, and and that makes things converge smoother to the final solution. Then the last that I know evolution was the CI NEB, so the climbing image NEB. Here the maximum along the pathway is identified, and for this maximum point one assumes that it has to get to the transition state. So instead of minimizing it along the NEB, it is maximized. So in fact the parallel component along the band is kept, but it is reversed in sign, so that this bead goes up and it doesn't go down. So then at that specific bead, so the maximum in energy, the NEB force is this one. So you see we have reintroduced the parallel component 2 times. Okay, so that is for it. So the climbing image then improves the gas of the transition state, and it is important in general if you have a molecular system to remove rotational and translational motion. In a condensed matter system, it's typically not needed, but I would say that the NEB is also probably not the best method to use if you have a liquid. It makes no sense because you cannot define the exact position of the reactant and end products of a liquid system. It's not a frozen system, so that But for a single molecule or a molecule on a surface, maybe if the surface doesn't change too much, then you can apply this. Yeah, so that is the input for the CI NEB. It's very similar to the input for the EB, just you change the method here, that has to be CI NEB, all the rest is similar. There is this additional section here that specifies when to start the CI NEB. It is a good idea not to start at the very first guess of your bits. So you let the NEB work a bit with, for example, IT NEB, such that you get a good guess of the maximum. And then after this number of steps, you start the CI NEB where the maximum is taken and it is pushed toward the transition state. So that is in here. This is CI NEB. So how many steps of IT NEB to be done before starting the CI NEB? As I said, you can optimize with sort of a geometry optimization or with MD with annealing, so where you reduce the temperature. This is not a real MD. You see the initial temperature is quite low. You are anyway looking for optimized structure, so at 0 temperature. And so you start with some motion just to get them more freedom to move and to find the better minimum, and then you reduce progressively the temperature. Okay. Yeah, so there's a pro and cons, already a bit mentioned. So if you have a clear definition of reactants and products and an obvious pathway, or you imagine an obvious pathway, this is a method that is very efficient, is extremely easy to parallelize. So you can get very good guesses of transition states. You can use it as a first guess of your pathway that then you refine with some other scheme. The drawbacks, well, if you start with an initial guess of your pathway, it will find the minimum energy pathway that it is the closest to that. If you have a completely different way to get to the same minimum, let's say for this way pathway, if you can go on the other side and you started something on this side, then it will find this pathway and not the other pathway. It will find only one pathway. So if you have a multiple possibility to get to the same minimum, and it will not find which one among the two is lowest in energy, so it will follow the bias that you have given. Yeah. It is a very important for a nice smooth pathway that the bits are not too distant. So one says the root mean square displacement, yeah, here is a bit overkilling, but not larger than 3 angstrom. So between 1 and 3 angstrom, the root mean square displacement between 2 consecutive bits. This in the output, at least of CP2K, you have this information. So how distant are the bits? And you see that some beads are too distant, and you might want to add an additional image to make it more uniform. Okay. Okay, that is some old example for the alanine dipeptide. Here the pathway goes along the rotation of these 2 angles. You in principle can define also collective variables and follow the collective variables rather than the whole set of coordinates. I mean, it makes no difference because the collective variables are defined in terms of coordinates. And you see here that's very similar results if you minimize with MD or DIS. DIS is with smoother pathway. Now this is the energy versus the bid index or the image index, so that you see that there are 2, say, transition states. And this is instead the comparison between the IT NEB and the elastic band for this system as a quite simple one, so no problem. Okay. Yeah, maybe this is something that I mentioned because sometimes people get confused by the results of NEB. It is very important when you define your initial pathway, even if you give more coordinates, that you keep the mapping of the atom one-to-one. So in NEB, the atoms, even if they are the same species, they are not equivalent. Every atom is individual, and it has to move from A to B, and it has to be this atom to move from A to B. So here the example is a small cluster of equivalent atoms, and it is in principle this state in energy is equivalent to this state. So you have a red atom in the middle and gray atoms around. But if you look at the numbering, they are different, and the pathway to go from here to the first solution and here and the next solution is different, because in one case it's just a switching between, so a rotational movement between these three atoms, and in the other case is a switching between 1 and 7. And the switching between 1 and 7 creates more distortion of the entire object, and the barrier is different. So the mapping, even if they are equivalent particles, it is very important. So that if you find strange things, it might be that you have switched two hydrogens. And then you had to have a hydrogen transfer from one part of the molecule to the other, that it's generally a large barrier. So that is maybe something to consider. Okay, so that I think is it for the potential energy search. Questions? Yes?
I was wondering with the NEB or NEB, is it possible to say start with 5 images, and then you know, okay, so the transition state should be around image number 3, and then you launch a new 5 images around image number 3, or between 3 and 4 or something. So that could maybe speed it up so that you don't have to go for 30.
So you want to do just a section of the pathway.
Right.
Yeah, you can fix in that case you probably need to fix the 2 endpoints. So you don't want to optimize the 2 endpoints, otherwise it will try to say, if your one endpoint is obviously not at the minimum, if you do something like this, it will try to minimize it, and being an endpoint, it will try to bring it to the minimum, and then you will have a very broad pathway with just a few beads. So if you fix the 2 endpoint, it should find the minimum energy pathway that connects these 2 endpoints. And why not? Yeah, it should work.
So the image is, let's say, or the maximum is between, let's say, 3 and 4. I can take 3 as initial, 4 as the final, and relaunch it again.
Yeah, but fixing them. Yeah. Yeah. Other questions? Yeah?
If there are more than 2 MIPS, and then all MIPS are outrouted, or you have to do many times?
You have to do many times. So if it, yeah. So you have to try to start with a different guess that moves you away from the first map that you found, such that you can maybe find a different solution. But the NEB itself will find only one. No, you don't know. Yeah. That's you have to put some insight from your side, because these things are difficult to know in advance. Yeah. Yeah.
I'm just curious whether you guys have dimer in CP2K as well.
Yes.
Well, are you going to talk about it?
No. But it is there. I think that methods like this, or how he said, is much more efficient than doing the dimer. So then you want to, so if it's a dimer, you sort of need to know where the transition state is, and you want to optimize so this climbing of the dimer along one specific mode.
Yeah. What I've been doing with WASP is that I start with CNEB, and then I'll get like 2 points, just like what you said, close to the transition state, and then I just
to optimize the transition state. Yeah, okay, that is for refining the transition state. Yeah, that is then you can do it. But if you start from blind guess, the dimer is gonna never work. So that's my experience. So
but possible in
Yeah.
CNEB as well.
Yeah. Okay. So then there's the definition of the transition state. So for a very simple system, you know, you check and then you look at the vibrational frequencies. For a more complex system, what I would suggest is to sit again on this structure that you believe is a transition state and start a number, even of MDs, with a slightly different velocity and check whether indeed this configuration falls an equal number of time into the two minima that it should connect. That is definition. This is the thermodynamic definition of a transition state, in the sense that it has an equal probability to end up in this minima. Okay. Right, so now let's go to how to simulate processes instead with molecular dynamics, with the help of molecular dynamics. In principle, we know molecular dynamics should explore the entire configurational space that it is available to your system, and it should do reproducing the right probability distribution of the configurations. And from the probability distribution, you in principle can determine everything that you want to know about the thermodynamics, so the free energy differences, the barriers that connect different states. But the problem is instead that the time you have to sample the space is limited, and even if you know that there is a next minimum or a new configuration, a new state that you should be able to reach, if you start from some equilibrium state, you can simulate also quite long without finding it. And here it is in this movie is a proton solved in water. Here is a Cl minus. Oops. Here is a Cl minus. In principle, it exists the possibility that the proton goes back to the Cl. It exists. It's higher in energy, but it is possible. It will never be obtained just by running MD like this. So the proton will diffuse around, jump from one molecule to another, so forming the hydronium ion that diffuses in the box, but this second state will never be obtained. And the reason is that MD is very good at sampling a minimum, so you get a lot of statistics if you start from some minimum and you stay there, but it is very bad in providing you statistics of part of the configurational space where there are transitions, because these are rare events, and statistically difficult to get information about these regions where the system spends very little time. So there is a real problem in distributing your exploration also to regions that have a low probability in order to acquire information there. So then you need some methods that enhance the probability to visit also these transition regions. So forcing it, so that is the idea. Also, if you see the transition at a given point, but you don't have enough sampling here, so the system jumps from this value of this whatever reaction coordinate to this value of this reaction coordinate. You most probably have a lot of configuration here, a lot of configuration there, but very few in the middle, and so to describe this region is anyway problematic, so that you don't have enough information. So then also to have the event is often not that common, because the barriers you have to cross are in general larger than a few kT, and then it is difficult for an MD to so the probability to cross such a barrier is exponentially decreasing with the height of the barrier, and so that becomes really an improbable situation. And the other thing is that standard, so normal free energy surfaces are rather complex. They might have many pathways with many intermediate and transition states, and yeah, such a situation, even here that it is only in 2 dimensions, is not easy to sample with a standard ND. There are considerations to be done in terms of entropic bottlenecks, so maybe there is a transition, the barrier is quite small, but to get there you have to go through a very narrow path, and it is improbable that the MD finds this narrow tunnel that, so it's kinetically difficult to obtain configuration that go through this, this channel. And then might be a multidimensional system, so many things have to change simultaneously, so it is a matter of multi-event situation, and again, the probability gets lower. With respect to NEB, you can, with MD, explore situations that you didn't expect. You don't put any specific bias. So in the NEB, you have to say, I want to go from A to B. But in principle, you might have completely unexpected results or unexpected product or pathway, as she said, that you absolutely cannot imagine, and they might be obtained just letting the system run. If a configuration is possible, it should be explored or sampled. Okay, so why this is so difficult? So the idea is that you can obtain your thermodynamic information if you have sampled the entire configurational space. So that in statistical mechanics term is to have the information about the partition function. So you set some thermodynamic variables, the number of particles, volume, and temperature, and you count all the configurations that belong to the given ensemble. So in fact here it is an integral. This is counting all configurations that, so it's the density of configuration that have the same energy, and this is in the canonical ensemble is weighted by the Boltzmann factor here, that this B is 1 over KT, so that is weighting the configuration with a given energy by the temperature. So you have to do this integral to get the partition function that if you transform, since the energy is a function of positions and momenta, if you transform this integral is an integral over the positions and the momenta, so this is an integral over a 6n dimensional space. That means you need to have information of each of the point in the 6n dimensional space, and have the calculation of the energy at each point, and then weight this with every configuration with, again, the Boltzmann factor, and you get your partition function. Yeah, that it's obviously very problematic because we don't have the time to explore such a large configurational space. But if you have it, generally what you're looking for is the configurational partition function, so the kinetic part is integrated out. If you have it, you have everything. So you have the free energy, and you can make every prediction about your system. Okay, this said, not really feasible, but it's already. We can already simplify things by saying, okay, we don't really need the absolute free energy. What we actually are looking for is differences in free energies. And that is making already things better, because what we need to calculate is this ratio between the partition function of a system 1 and a partition function of a system 0. This contains all the information, entropic and enthalpic information, contribution are all included here. And what is meaning comparing two different states, yeah, it might have different meaning. You might have states that differ because they are sampling different parts of the configurational space. So this is the volume of the configurational space, so they belong to different parts. So you want to estimate the different probability of being in a given region of the configurational space or in another. They might be characterized by having different Hamiltonians. So let's say different charge or a different interaction between molecules. Or they might have a difference in some thermodynamic parameters, say the temperature. So that are possible ways of imagining different states. So what you can do as a way to calculate this ratio is to use a perturbation formalism. So you run in one state. In this state you have, let's say, this given Hamiltonian H0. And you want to know, have information about also an additional state, that it is the one state where the Hamiltonian will be H1, that it is an H0 plus some perturbative term, so a delta H. And so you want to sample in the H0 ensemble, so you do your simulation using the H0 Hamiltonian. And that means that you collect the probability distributions P0, that is the probability of having this configuration, so with R and P, in this ensemble. But you can obtain this free energy difference as, so in principle we already wrote, it is the ratio, it's given by the ratio between the partition function at state 1 and the partition function at state 0. But if you rewrite H1 as we had it above there, so it as H0 plus delta H, we find out that this ratio can be understood as the ensemble average in the ensemble H0 of this function, so the exponential of delta, beta times delta H. So this is it. So that means that we can obtain the delta A, so the difference in free energies, just sampling in the ensemble obtained with H0. So we take the ensemble average of this quantity in the, by sampling in this ensemble. What this means means that you do the molecular dynamic simulations with H0, and at each position that you obtain, at each configuration, you calculate delta H. So you have the coordinates obtained and the momenta obtained with H0, and there you calculate H1 so that you obtain delta H, the difference. You make the average, and then you, if your simulation is long enough and has sampled completely the configurational space, you have obtained the, this ensemble average. You can do also for the ensemble average of another function in state 1, just sampling in state 0 and calculating these ensemble averages. Okay, this very nice, one can use it. The thing is that it works very well if the two ensembles have domains that overlap strongly. So if you sample the ensemble 0, you also visit a lot configurations that are important for ensemble 1. Otherwise, you will have a too poor sampling of ensemble 1, and so this is a situation if the probability distribution of ensemble 1 and ensemble 0 are very much separated, you will have very low information, very poor information about the tails here that are the important part for the ensemble that you want to compare. So things like this, or a situation like this, where there is a strong overlap within the important regions of the two ensembles, is a good situation where you can use this method. If the overlap is very poor, or the ensemble 1 has a really tiny volume with respect to ensemble 0, means that this volume here will be very poorly sampled by sampling the ensemble 0, and then in these two situations you will get poor information and a bad evaluation of this ratio. Okay, that is one way to do it. It's just simple molecular dynamics simulation, so that you can obtain some free energy differences. Other methods instead rely on the definition of some collective variables. So the idea is that you reduce the dimensionality of the system. That means you put a bias, or you put your insight in what is going to happen. Yeah, it has also several drawbacks. If you fail in defining the right collective variables, you find probably processes that do not reproduce the real free energy profile. Defining collective variables means that you think that along the specific collective variables you need to enhance the sampling, and you assume that all the other degrees of freedom fluctuate and sample the entire space that belongs to them completely during the movement of the slow collective variable. So that you define slow motion, slow modes, and fast modes. The fast mode, you assume that they are sampled completely along your MD, that you don't have problems in sampling them. If you miss some of the important modes or the important collective variable, obviously you will find results that are not correct or not accurate enough. Collective variables are in general function of the coordinates. There are cases where collective variables have been introduced that are functions also of electronic structures, so but there it is more complicated because you have to go and sort of work with wave functions. I will not introduce them today. But typical collective variable is a function of some coordinate, like an angle, a distance, or something that you can be a combination of many of these angle, distance, coordination numbers. We will have a look at some of them. Yeah, so the dangers behind choosing collective variables are many, and you have to learn by using them what might happen. Then if you have this, you then restrict the sampling to this subspace of the collective variable. You can have more than one, and in the end what you want to obtain is the density of states for a specific value of the collective variable, so that, or of the set of collective variables. So then your parameters are number of particles, volume, energy, and the value of the collective variable. So here you see the integral is then, so this is a density of state in a microcanonical ensemble, so the potential energy has to satisfy the constant value of the energy, and the collective variables that are defined in terms of coordinates have to satisfy the given value that have been set. So this is the number, so this is counting the number of configurations that correspond to the fixed parameters. This is in the microcanonical ensemble, this is in the canonical ensemble. Instead of having the delta function here, you have the Boltzmann factor, and this is the same. In the end, you will find the free energies that come from this partition function that are at specific values of, that consider this, the change of these collective variables. So that means that the first property that you require from the collective variables is that they distinguish clearly among the states that you want to compare. So you need some number here that doesn't matter what the number is, but it has to be different number between state 1 and state 2. And the fluctuations of this collective variable at equilibrium have to be smaller than the difference between the two values at the two different states. So this is a rule because that it is very general, otherwise you will have fluctuation of the collective variables between the two states already at equilibrium, and so that will not help you in distinguishing the two different states. Okay. So this said, you can, working with these collective variables, you can force the sampling of regions that have a poor probability. So you try to make your sampling uniform along the entire profile of the free energy, so having enough information, so enough statistics also for regions where the probability is in principle lower. You have to take into account that already a difference in 5 KT makes a huge difference in sampling. So like one state that it is 5 KT lower will be sampled 1,000 times more than a state that it is higher. So then it's really a problem of making the sampling uniform. So then if you restrict somehow so you want to sample now this collective variable. This is a dihedral angle among carbons. Then you say, first I focus on these values of the collective variable, so I restrict my sampling for this value. Then for these values, then here, and then there. You have to take care in this type of stratification schemes that the regions that you separate, they overlap. And if you do that, there are techniques to then recombine the different regions, recombine the probability distribution that you have collected, and obtain a probability distribution that, say, it's not biased. The only bias that remains is the fact that you assume that the pathway is along this coordinate. That you cannot change. That has to be, this is fixed in your simulation scheme. So these methods are called umbrella sampling and then the reconstruction. I mean, I don't describe them here, but you find a lot of literature or books even, because they are all methods to reconstruct the unbiased profile. You can use WAM or other schemes, and yeah, it's very common. The restriction here, and we see also in other cases, is that it works fine with in one dimension. Already when you have multidimensional collective variables, it's more problematic to collect the information. And the multidimensional problem is very well known, so that sometimes one assumes that one can just use a one coordinate, and if you use only one, as it is here, you describe the pathway only using the q coordinate, and you forget about the q prime, you might obtain really wrong value of the transition states. So you need, so the goals that are, you have to have all the coordinates that are important. They should be, the pathway described by this coordinate should be reversible. And you have to include the higher dimensionality if it's needed. And you have to be able to characterize properly also transition regions with these coordinates if you want the barriers. Yeah. This is the case. So if you have this system and then you try to use only the one coordinate, so only the xc and not the xc prime, then you will find the transition state in the wrong position. So you will find the transition state here, while the transition state is there, that is almost overlapping with the basing of attraction of the minimum A. So therefore, just using the xc you will not find it, or you not find it correctly. But if you would do it in 2 dimension, you would recognize that you can move also in this dimension, and the transition state is actually almost the same place in Xi, but in a different place in Xi prime. That's, yeah, so and it's something that nobody will tell you, and you have to know your system and try to find what is needed to simulate the right processes. Okay, so these are just examples of obvious collective variables like distances or a function of distances. Coordination numbers are very nice and general collective variables. They tend to keep the bias quite light. Or you can invent any function of your coordinates that is meaningful to describe your system. So that is really open what a collective variable is. Often in codes some are already implemented. Sometimes you can invent new one just combining those that are already implemented. Sometimes you might want to implement new ones, but it is quite a trivial thing to implement a new collective variable. It's just analytical function of the coordinates. How to use them in CP2K? You have to go to the subsystem section and define them. So you can have as many as you want. Every one is defined with its own section called var, and then you can look at the list of that are available. And you can specify the parameters that are needed. Every collective variable needs obviously different parameters. Sometimes you need, for example, like a cutoff, and then you have to specify maybe the units. So you have to look which are the assumed units. Yeah, but you have to know the analytical expression of each collective variable to know which parameters to set. So these are just a few examples. An obvious way to use collective variable is fixing their value, so fixing a constraint. So you want to have this collective variable at a fixed value, and then you want to sample all the possible configuration that correspond to this fixed value of that specific collective variable of more than one. Then you can fix constraint or restraints. And then you have to go to the motion section. Go to the open section constraint and give that this is a collective constraint. So you can also have different type of constraint, like fixing specifically the position of one atom. This is instead a constraint that involves more atoms, so it is a collective constraint. It is an intermolecular constraint, and the definition is given by the index of the call bar that you defined in the subsystem section. So the index will be just the sequence in your input. So the first one that you write is the call bar 1, the second the call bar 2, and so on. You can have a fixed constraint, you can have a changing constraint. So you want that this constraint goes from value 5 to value 10, and you want that it grows with a given rate, and then you can have this changing constraint. Or you can have a restraint, so there's less than a constraint. So you fix, like you define harmonic potential that restrain the value of the collective variable around the value that you have given as a target. And how strong it is restrained depends on the constant, the harmonic constant here of your potential. Yeah, these are useful for many different things. Constraints, if you want to explore the state at a fixed value, or if you want to remove some motions because they are too fast and you don't want to sample them. So that there are different reasons to use constraint, also to explore potential or a free energy pathway, just changing the constraint or changing the value of the collective variable along a given sequence of value and sampling. To introduce constraints in MD is very simple. That you define an extended Lagrangian where you have additional terms here that are the conditions on the constraint. This is with the velocity Verlet algorithm that has been introduced on Monday. It is very easy to implement. There is a very standard technique that it is the shake and rattle algorithm, where you modify the force on your atoms, introducing the force of the constraint that will impose that the constraint is maintained. For the restraint, it's even easier. It's just an additional potential. You don't have even to do this. So it's just add the potential to your standard potential. You have to take care that the constraint means, I mean, not only, I think it's just behind, yeah, it's, you have two conditions. One is the condition on the coordinates that have to satisfy the value of the collective variables that you have defined, and the other condition is on the velocities, because along this, so for this variable the velocity has to be 0. And this will be also a combination of the velocities of the particles that are involved in the definition of these coordinates. You want that the value is fixed and its velocity is 0. So then you will have in this shake and rattle algorithm, you will have a condition, so something that it is a force here, additional force term to fix the constraint, and then you will have additional force term here to fix also the velocity. And you find the coefficient to determine these forces as a linear combination of the derivative of the definition of the constraint with respect to the particle position, just by implementing this algorithm. Okay. So okay, that's maybe I go a bit quicker here. This is another method that is very common to use, the thermodynamic integration with constraints. And this you can also do it with whatever molecular dynamic code that implements constraints. You can, in the end, recover the free energy profile here. So actually, the free energy difference between two states, just integrating the potential of mean force. And if you implement constraints, you find that the potential of mean force, that it is this ensemble average of the derivative of the Hamiltonian with respect to the definition of the collective variable. So this ensemble average can be obtained, I go a bit quick, can be obtained directly by the ensemble average of the Lagrangian multiplier that you have in the Lagrangian when you introduce constraints. So you extract from your simulation along your MD the Lagrangian multiplier, and you make the average, and then you have the value of the potential of mean force for this specific value of the collective variable. Then you do this for many values of the collective variables you have defined, and for each of these values, so you fix the constraint, you collect along the MD the Lagrangian multiplier, you make the average, and you have your value, and then you do it along the pathway, so for all the values that you need to sample, and then you simply integrate, and then you get the free energy difference. This is called thermodynamic integration. It's also a very common scheme to obtain free energy profiles along one specific reaction coordinate. There are some care that you have to take, because obviously you have a sampling that it is biased by the constraint, but there are ways to correct for this bias such that from the conditioned sampling you obtain an unconditioned profile. It's also very standard methods. Okay, so difficulties here are the fact that if you have more than one collective variables, then you start having, so two, then you have a grid that you have to sample. If you have a tree, then you have to sample a volume, so that start becoming expensive. So for multidimensional schemes in practice. Okay, so that's the questions. Because now I go to the metadynamic stuff. No, these are methods maybe that you already knew, so just that you know that you can do it easily also with CP2K. So the metadynamics is also probably now quite known and used. It is implemented in CP2K. You can use, as has been already mentioned, in connection to other code that use CP2K as a library. I will go through a bit the idea of the metadynamics. That is to be able to bias your sampling, again defining some collective variables. This remains a task that you have, so to define the correct collective variables, and biasing in the subspace of this defined by this collective variable. So in this subspace, you add a potential that prevents or makes it more difficult to repeatedly visit always the same configuration. So if you have sampled already a given region of the space, of this lower dimensional space, then you are forced to move to another region by this additional potential. It's like a penalty potential that changes the probability of a region that has been already visited. This we call the metadynamic potential, and it is constructed, as you see here, by adding small bits of potential, also of positive potential or repulsive potential, at the positions in the space of the collective variables that have been already visited. And you grow it bit by bit, so not just changing abruptly, but just letting the system evolve after you have moved a bit the situation, such that the sampling remains smooth and continues, and also all the other variables, so collective variables, all the other degrees of freedom that you have not included in the collective variable definition have the time to be sampled sufficiently. That it is absolutely crucial, because if you move too fast and you have not sampled the orthogonal degrees of freedom, you have the wrong probability distribution. So the weight of a given configuration is the number of microstates that belong to this configuration. So all the other movements have to be sampled because they count as macrostate that correspond to the same position in the low dimensional metadynamic space. Okay, so this is the very general message. In the end, yeah, you have this potential that you add typically, or it is done by adding Gaussians. It is very easy to treat Gaussian, so why not? So that's just a small repulsive potential. It can be multidimensional. So in principle, there are no restriction on the number of collective variables. You increase the dimensionality of the space that you have to sample if you increase the number of collective variables, so you have to expect a longer time to sample it. It's obvious, and yeah, and then probability distribution that you obtain can then be used to reconstruct the free energy surface, underlying free energy surface. Okay, so this is the scheme. So you start from an equilibrium state. We suppose that you are already sampling there. It's a very good idea to start with a standard MD, such that you know where you are, you know how big are the fluctuations at equilibrium. Just don't start with directly with the metadynamics. It makes no sense. You want to know what happens if you just run for a few picoseconds. And then you know which are the variables that you want to enhance. And you then need to know which are the equilibrium fluctuations of these variables. And then you start activating the metadynamics, meaning you start feeling the minimum where you are with this repulsive potential. This repulsive potential, after some time, pushes the system towards the lowest possibility in energy, or in free energy, to escape. So it finds some transition regions and it moves away. As I said, afterwards, by looking at what you needed to escape, you can recover the depth of this potential well, or this free energy well. That's the idea. So that you looked at how much effort you have to put into the system in order to move away, and then from this you recover the free energy. We are always talking, now it's written here A, but we are always talking about free energy differences. There's no indication of the absolute value of free energy. Here is just the difference in free energy between a minimum and a transition state, or two different minima. It's always talking about differences. Ideally, you want to fit your MD such that you cover the entire space of this possible variation of the collective variables, and after a while you have a situation where you have a flat surface. So here you have filled both wells, and now you are on top here, and you're adding a potential, but this profile is now flat. So the system will move back and forth between these two just by adding more potential, and nothing actually changes. Actually, the difference between minima and transition state will remain always the same. You increase, but since you are in a flat situation, so actually your result doesn't change, so you converged. In this respect, the error that you have when you stop, if you are in this situation, so the error in the evaluation of the free energy difference is the size of your bit of potential. So this is the corrugation that remains once you are in a flattened situation. If you do everything correctly, so you deposit this potential slowly, so that means that the deposition rate is much slower than the time step of your MD. So you do it one deposition every n time steps. And if the deposition rate is slower than the time that it takes for the collective variable to diffuse over the entire space, and you have used small enough hills, then this should be what you obtain, and you're happy because you have your results. Yeah, this is a very old movie that it is explaining very well. So you start with a minimum, you find the first transition state, so the lowest, but this might bring you to a minimum that it is not the lowest minimum. But you continue, now you are flattened, in principle you go back and forth, you see here. So where the blue line changes where your dynamics is. And finally you find also the next transition state, and then you are falling in this region here, and then you are exploring this region as well. And until you arrive at the same level here, and now you should start moving from here to there, you see, and then from here to there. Okay, it's stopped, but then you would move it back, and you will go on like this. Okay, the algorithms that are implemented are just increasing. So you can use this Lagrangian scheme. So you extend the Lagrangian, introducing some variables that represent the position in this dimensional space, in this metadynamic space. And these variables are affected by this metadynamic potential, so they feel the forces coming from this metadynamic potential, and additional they feel the forces that connect them to the real system. So the real system will take these variables at the value of the minimum, because the free energy tells that the system has to remain at the equilibrium. So that is the potential, the free energy forces, and the metadynamic potential pushes them away. So the combination of these two things makes the exploration thorough and slow enough, just so that you can sample all the possible configurations. You collect then this potential, and then you obtain this thing, and then from this you obtain the free energy profile. Okay, so if you do the Lagrangian, extended Lagrangian scheme, these are really dynamic variables, so they also have a mass and a velocity, so they have a dynamics by themselves. What else? Okay, this is some information about the accuracy. In principle, the accuracy doesn't depend on the profile, it depends on the rate So if you put this additional potential too fast, you will get some inaccurate results because you don't have the time to sample the orthogonal degrees of freedom. It depends on the size of the hills. If the size of the hill is larger than the typical fluctuation of your collective variables or of the features of the free energy, then you flatten them down and you don't see them. So the resolution with which you get the profile depends on the size of your hills. If you have something that it is very large, you cover anything that it is at lower resolution. What else? So the height of the hills obviously is also important, has to be smaller than 1 order of magnitude smaller than the minimal barrier that you want to see. If you make something very large, you are creating barriers by putting hills. So that's then you get something strange because you are modifying the profile with these hills rather than following it in a smooth way. What else? So you can check the error looking at the flatness of your profile at the end. These are a sort of warning. I think that more or less I already mentioned them. So the choice in the end, the choice of the collective variable is the most crucial point. Then you can always repeat the simulation, change the hills size and check that they converged. Typically, you can start a simulation with very large hills and then you explore very fast. You have a very bad estimate of the free energy and so, okay, now I know more or less what there is around and I come back and do it again and maybe focus on one part of the space and get better information. Depending also a lot what you are aiming at. If you look at mechanisms and you are not too much interested in the profile, then you can be more easy or with the choice of the parameters. Instead, if you want a precise evaluation of the free energy barriers and the difference among minima, maybe you have to be more careful with the choice of the parameters. Yeah. Okay, and then if you use metadynamics, in the end, your proton will go back to the chlorine, even if it is not a very stable state. It is a state, and it will be obtained. So that's the idea. So if you decide that this parameter, this collective variable, has to change, it will change, going also to states that are not given to be the absolute minimum. Okay, the input, and maybe, I don't know, it's maybe time to stop. Metadynamic input in CP2K. As I said, you can link CP2K to plumed and use then for the metadynamics whatever is the input in plumed. You just have to put in the input here that you want to use metadynamic with plumed. Instead, if you use the metadynamics of CP2K, then this is the input. You have already defined the collective variable in the subsystem, as we have said before. Now, instead of the constraint, you have in the metadynamics section that is inside the free energy section, that it is inside the motion section. You have for example, the definition of the metadynamic variables, and you see that you have to specify which collective variable is corresponding to this metadynamic variable. And then if you are using the Lagrangian scheme for each metadynamic variable, you need to define the K, so the strength of the harmonic potential that links it to the system, and the mass. This instead is the size of the potential hill in the dimension of this collective variable. The units of this value depends on the definition of the collective variable. Here they are not specified, makes no sense. But if this is a coordination number, this unit will be number, so just a number. If this is a distance, this unit will be Bohr, because it's the internal units of CP2K. If this is an angle, it will be a degree, a radiant, or whatever. Depending on the definition of the collective variable, this has a different meaning. And you have to specify this for each metadynamic variable. This scale, so this size, as well as the temperature of the collective variables or the number of time steps between the collocation of consecutive metadynamic hills, or the size in height of the hill. These are things that you can always change along your metadynamic run. What you cannot change is the definition of the collective variable. So if you want to change the definition of the collective variable, then you have to start a new run, because you are sampling a different space in practice. Okay, what else? Yeah, so that is more or less it. Okay, you can run metadynamics without putting hills. That is why? Yeah, because this you monitor your collective variables. So you can do it also just writing a script, taking your trajectory and calculating the value of specific collective variables. You can do it using this section. You can then define 100 collective variables, and along your molecular dynamics run that you already did because of other reason, you can explore the fluctuations of the variables. This is in general very important to do, or is useful when you have to decide what to use as a scale. So then you know how much these variables fluctuate, or you can use it, you know that there are different states, you start an MD at different state and you look at the values of the collective variables and you check whether they are different between state 1 and state 2. Okay. I think that from my side it's fine. There are some examples, but I think that we can stop here. Maybe you have questions. Maybe not. Okay, if not, then yeah, I'm done. Good.